In this video tutorial, I'll give a brief demonstration on how HALCON 13 can be used together with the SP1 stereo vision system to perform 3D shape detection. HALCON 13 features many improvements for 3D image processing, but most importantly, its ScanTL interface now supports 3D point clouds, which greatly simplifies the integration with the SP1. For this tutorial, I'm going to use our Carmen stereo camera, which has been mounted here on a tripod and is looking down vertically on a table where we have placed a cylindrical can. The Carmen camera is attached to our SP1 stereo vision system, which does all the stereo image processing, and the SP1 itself is connected through gigabit Ethernet to a computer that is running HALCON. So right here I'm running HALCON on Linux, but actually everything that I'm going to show also applies to HALCON for Windows. We start by verifying that the GenTL producer is installed correctly and that the computer is receiving image data from the SP1. We do so by opening up a new image acquisition and by having a look at the available interfaces. So right now we still have all possible interfaces here in this interface list because we haven't yet run interface detection. By clicking on the Auto Detect Interfaces button, most of these interfaces should actually disappear, but we should still have the GenTL interface, which we're going to select. If we switch over to the Connection tab, then we can see a list of different detected devices. So these devices, they're actually all virtual devices for one and the same physical SP1 that is connected to this computer. So each of these virtual devices provides a different type of data. The first one that we have here is the disparity device, which provides the disparity map, which is the inverse depth map. Then we have here the left camera image, we have the 3D point cloud, and the right camera image. And we also have this first entry here, which does not have any additional name. This is a device providing a multi-part data stream, meaning that it contains several different types of data, and actually this device contains all the data that is provided by the other individual devices. Multi-part data streams are a new feature in HALCON 13, which greatly simplify the synchronized acquisition of different types of data. So let's verify that HALCON is actually receiving data. We can do so by selecting the left camera from the list of virtual devices and by pressing the live preview button. Then what we're getting is an actual live view of what the left camera is currently recording. So as we can see, the camera is observing this cylindrical can that we have placed here. And this is actually going to be the goal for this tutorial, to detect this cylinder by just looking at the 3D depth data that we receive from the SP1. Likewise, we can also get a live preview of the disparity map as it is being computed by the SP1 by selecting the disparity virtual device and again pressing the live preview button. Now, in this grayscale image that we get here, it's actually hard to recognize something. So what we can do is we can select a lookup table for color coding. The cyclic temperature color scale actually works nice for the disparity map, as we can see here. So in this case, red hues correspond to close image points and yellow hues correspond to image points that are a little bit farther away. We can also try to have a look at the point cloud virtual device, but if we do that, we're not getting any preview. This is because this virtual device provides 3D floating point coordinates, which cannot easily be visualized, at least not in this image acquisition dialog. So much about experimenting with this image acquisition dialog. Now let's move on to the actual programming. So for this tutorial, what we're going to do is we are going to modify the example program that is provided with the SP1 software release. So let's open the example for HALCON 13 and then let's try and run it. So what we see, this example opens up 3 different graphics windows. But let's first disable this code following here. Okay, the 3 different windows that we have here show the image of the left camera, a color-coded version of the disparity map, And here on the right we have an actual live visualization of the 3D point cloud. Okay, so let's stop this program and let's have a look at what this code is actually doing. Right here at the very top we have one open frame grabber statement, which is actually opening one of these virtual devices. Now the device that it opens is the one that ends with a slash. Now, as I said previously, this is the multi-part data stream device. By accessing this multi-part device, we can get actually all the data that is provided by the other virtual devices, but we can do so in a synchronized way, meaning that all of the different types of data that we're acquiring always correspond to the same point in time. Right after that, we have some code for initializing the graphical output, where we're going to skip over. And then the next interesting line again is here this call to grab data async, which acquires one frame from this device. Now, grab data async actually uses a separate thread for image acquisition, which is why there is a call to grab image start somewhere before that. The alternative would be to use the grab data function, which does image acquisition without using another thread. The code below then separates this multipart frame into its individual components. There is the left camera image, the disparity map, and then 3 different maps containing the x coordinates, the y coordinates, and the z coordinates of the 3D point cloud. After that, there's some code for visualizing the left camera image and the disparity map, which we're again going to skip. This is where the processing of the 3D point cloud starts. First, the threshold function is used on the z coordinate map to create a region that contains all points up to a depth of 3 meters. Then the reduce domain function is used with this region in order to select all points that are within this permitted depth range. It is only necessary to call reduce domain for one coordinate map, which is why here it is applied only to the x map. The individual coordinate maps are then combined into one 3D object model by using the xyz to object model 3D function. And then finally, this 3D model is displayed using the disp object model 3D function. There's also another way to display this 3D model by using the visualize object model 3D function, which is here commented out. But we can switch over to this function and rerun this program. As we can see, in this case, we no longer get a live preview of the 3D point cloud, but rather we get a still frame. But now we are able to interactively zoom and rotate this frame, and we can get a rather clear view of the 3D contour of the cylinder. Now, as we will be running this program several times, the first real modification that we're going to do is to select an appropriate default pose for the visualization. We can do so by editing this create pose statement at the beginning of the program. And now here in this example, the virtual camera is actually looking at a slight angle from a larger distance at the observed object. Now we can change that to have a closer and more vertical view by setting here the lateral offsets to 0, by reducing the distance, and by also setting the angles to 0. So let's rerun the program and have a look. As we see, this new camera perspective is actually a lot more suitable for this example. Now let's continue with the actual image processing. If we want to detect this cylinder, then the first thing that we have to do is we have to segment it from its background. In this case, this is actually rather simple because the cameras are looking down approximately vertically onto the table. So if we want to separate the cylinder from the table, then we can apply a simple thresholding operation to the observed depth values. As we have seen before, this example already performs a thresholding of the depth values, so we can just go and modify this. Now, here in this case, the cameras are approximately half a meter away from the table. So let's first try out a threshold of 60 centimeters and rerun the program. So all of the table is still there, meaning that this threshold was not strict enough. So let's reduce it to 50 centimeters and retry. So this seems to have been too strict, as most of the cylinder has disappeared. So let's try out 55 centimeters instead. This threshold seems to be just right, as all of the cylinder is still there and all of the table has disappeared. We should be aware that there's only the upper half of the cylinder visible, because this is the only portion that can be seen by the cameras. Just to improve the error robustness, we can also set a lower threshold for the depth. We can try out a threshold of 50 centimeters and rerun it. And as we can see, this actually cuts off some part of the cylinder. But if we set this to 45 centimeters and rerun the program, we can again see that this threshold seems to be just right. Let's continue with the actual object detection, for which we're going to use the function segment object model 3D. This function is able to detect a set of known geometric primitives from the 3D point cloud. We pass it the 3D object model that we created, and for now we're going to use the default parameterization. And then this function is going to return a new 3D model that we're going to save in the object segmented variable. Because we're trying to write good code, we're also releasing this object model again by calling the function clearObjectModel3D. And finally, we're going to display the detected 3D primitives by also passing them to the visualizeObjectModel3D function. So let's give this program another go and see what it does. As we can see, it actually detected several cylinders, which each approximately represents some part of the observed can. But there are some significant outliers. The reason for this behavior is that we have been using the default parameterization for the segment object model 3D function, which does not work so well for our example. The parameters that we're going to adjust are the min area, which is actually the minimum number of 3D points that are required for detecting a 3D object. Then there's the maximum curvature difference between two surface points and the maximum allowed orientation difference between two surface normals. For the min area parameter, we can actually select a very high value of 10,000 because we have a very dense point cloud. And for the other two parameters, we're going to choose values of 0.1 and 0.2, which are parameters that I have successfully tested earlier. Now let's rerun this program and have a look. Now this time the cylinder has been detected very nicely. And it should be noted that we actually did not instruct the segment object model 3D function to search for cylinders, but rather it searches for known geometric primitives, which can be planes, cylinders, or spheres. And it correctly identifies that what it's looking at is a cylinder. In order to improve the visualization, let's also visualize the table surface. We can do so by copying the existing code from above that does the depth thresholding, and we can apply a higher threshold that will also include the table. We can then create a new 3D object model from these thresholded coordinates, which we're going to call Object All. Of course, we should not forget to release this object model again. And then we're going to use this model for visualizing the 3D point cloud. So let's rerun the program and have another look. This time we can get a much better view of how well the cylinder has been detected. If we take a close look, we can see that the cylinder almost touches the presumable plane of the table surface. To show that this program also works well for other orientations of the cylinder, we can just replace the can and rerun the program. The cylinder has been detected just as well in this other orientation. Let's replace the can again and try out one more orientation. As we can see, the cylinder has again been detected just as well. So this concludes this video tutorial. If you want to learn more about the SP1 stereo vision system and its possible applications, then please visit nerian.com or feel free to contact us. Thank you for watching.